Last class, we discussed about EAS reactions. To brief you some of them, you can see benzene indulges in reactions where you have X2 in the presence of Lewis acid like AlCl3 to give halobenzene. It can involve with concentrated HNO3 with concentrated H2SO4 together present to give something called nitrobenzene. Then with only concentrated H2SO4 or oleum, you will get sulfonation. So we'll get this as SO3H. And then we discussed about RX in the presence of AlCl3 or any other Lewis acid. We would end up getting this R group here. And last reaction which we learned on a similar line was if you have R C double bond OX in the presence of AlCl3, which will give us C double bond OR. This reaction is called Friedel-Crafts alkylation, and this is Friedel-Crafts acylation. The basic mechanism in all of these are the same, that they all will have an electrophile being added, getting an intermediate like this. This intermediate, when you write in terms of their resonating structure, I mean hybrid structure here, so it will be EH with delta positive moving across these three places. We call it as a valent complex, arrhenium complex, okay, or sigma complex. These are the names for this complex, okay. And rate of EAS mainly depends on stability of this complex. Stability of complex. Okay. These are the fundamentals which we learned the other day. Got it? Then we emphasize on the fact that there are certain drawbacks in Friedel-Crafts alkylation. That is, it can undergo polyalkylation. So, for example, if you have benzene and you treat this with CH3Cl in the presence of AlCl3, first you will get methyl benzene, but the next reaction would continue with this methyl benzene to give further these kind of products. Multiple products can be formed here. Ortho para meta directing products like this. Or even these can react with further CH3Cl with AlCl3 to form a major product like this, which is called mesitylene, right? So it becomes difficult to control, right, the alkylation to one product. So you will get multiple products here. One way to control is what you can do is you do acylation first, like CH3C double bond O Cl in the presence of AlCl3. In that case, C double bond O CH3. This is excess, so you will get this one. But further reaction of this acylation does not take place. This will not take place. Hence, this is the only product which you will get. So from this product, in case if you use Clemenson's reduction like zinc mercury amalgam in concentrated HCl, then that C double bond O get reduced to alkyl part. So first an acylation followed by reduction will lead to the formation of alkylation. So direct alkylation is not preferable, but you can go in this particular route. This is what Friedel-Crafts reactions suggest, right? And Friedel-Crafts reactions can be Now, if you notice, in the case of Friedel-Crafts reactions here, so we will get this as an ethyl benzene form, right? This way, Friedel-Crafts reactions can also be done with alcohols in the presence of either Lewis acid or HF at 0 degrees Celsius. There also you can get a product like this. You can take an alkene, you react with PPA, polyphosphoric acid at 0 degrees Celsius. Even then, you will get a product like this. Got it? You can have halogen here with AlCl3. It can undergo rearrangement also, and then you can get this product as major product. So these are all the alternative methods by which you can get alkylation done on benzene. Not just that, within the molecule, for example, if you have like this, I have a double bond O and OH here, and then you're treating this with dilute H2SO4. Then what do we expect here is that in this case, we can have double bond O and OH2 being made here. OH2 goes as a good leaving group and it will form an acyl group here. So like this, we can get double bond O plus. When a positive charge is forming within the molecule, internal attack is favorable. So from here the attack happens. So you can see the ring size 1, 2, 3, 4, 5. A 5-membered ring will be formed here like this with a double bond O. Okay. And this can be further reduced using zinc mercury amalgam, and that keto form will go into alkyl form this way, right? Internally also we can reduce this product into alkane. So guys, from the basics of benzene, these are the terms you should know. A part of the preparation, these are the things you should definitely know. Okay. Now, before going further into details about why in certain cases Friedel-Crafts reaction works and in why in some cases Friedel-Crafts reaction does not work, or in generally in which cases EA's reactions work, first you need to understand one thing. If you have a group here, this group here, and if this group is being replaced by something new, like this, some new group has been replaced. So this is called ipso substitution. Substitution. That means a functional group which is present on benzene is being removed and some new group has been attached at that position. Such kind of substitution is called ipso substitution. Instead, let's say I have some electrophile, something like Y plus here, correct? And it is getting attached on either ortho position or para position. This position is called ortho. This is called para position. Okay. Then we say that, right? The group G is allowing electrophile at ortho and para position. Hence, group G is ortho-para directing group. We call this as ortho-para directing group. Okay. So understand these terms carefully. Next, in case if you have any Y plus and then this group is only attaching here at Y position, I mean at meta position, this is called meta position. Okay, then we say the group G is meta directing group. Got it? When such things happen, let's understand that there are three type of substitutions we understood here. One is a ipso substitution, which means within the molecule where the group is present, that is being removed and the new group has been attached. Or second type is it can go at ortho para. Usually what happens, only ortho or only para is less likely to form. They will always be ortho para forming at different compositions. Got it? If ortho is major, para will be minor. Para is major, ortho will be minor. Hmm? Or there would be cases where only meta is forming. Ortho para are, less likely to form in that. Only meta is forming. So three situations you will get always. Okay. Which cases you will notice that orthopara directing is happening, in which cases meta directing is happening. Let us understand that logic first. Okay. So first one is OP directing groups. Which will be these OP directing groups? The first of the kind of OP directing group is lone pair carrying groups. Lone pair carrying groups. What does that mean? See, if you have a benzene and directly there is something like NH2 connected here, where nitrogen has a lone pair on it. Okay. Then, if an electrophile has been sent towards this molecule, chances are that with respect to this NH2, the electrophile will come at this position, at 2 position, or NH2 will electrophile will come at 4 position. At 2 position, you call this as an ortho substitution, or this is para substitution. These are the two terms you must understand, ortho and para. Why is no meta forming here? Let us understand that through mechanism. See, whenever NH2 is present, the lone pair present on NH2 is always in resonance with benzene ring here, because of which you will see negative charge will come here, NH2 plus will be here, and that negative charge again through resonance will move at this position. You will get negative charge here, double bond, double bond, double bond, NH2 plus here, and again negative charge will go here, pi bond will move here, negative charge will come, double bond, double bond, double bond, NH2 plus here. Now finally that negative charge will go here and you will get NH2 back. So out of this, what do we understood is that electrophile, if at all it is approaching, it could approach at these three positions. Now you can see this is ortho position, and this is para position. And that's the reason whenever there is an electrophile approaching to a lone pair carrying group, it will always approach at ortho and para position only. It do not approach at meta position because electron density is more at ortho and para position to invite that electrophile. Okay. Now, is it only for groups like NH2? Not necessarily. Even if you have a group like halogen, X halogen, which is fluorine, chlorine, bromine, iodine. Naturally, halogens are withdrawing, but yet because they carry lone pair, if an electrophile has been invited, right, or trying to get substituted, it will only facilitate at ortho position and it will facilitate at para position. Got it? Now, what are the other cases which likely to do this way? Now, let us see. This is case B. Okay, sorry, case 2. Write it as case 2. So, if you notice case 2 here, other than double bond, other than lone pair, even if you have a double bond, or triple bond of carbon-carbon form, of carbon-carbon bonds, if you have, still you will have a similar result. That is, benzene having CH double bond CH2 right? If this is been asked to attach an electrophile, you will get this as CH double bond CH2 with an electrophile here at ortho position, and CH double bond CH2 with electrophile at para position. These two are the forms you will notice. Got it? Third case, if you have any alkyl group, if you have any alkyl group, that is, if you have benzene with CH3, correct, or benzene with any CH2CH3, clear, benzene with isopropyl, benzene with tert butyl, like this. All of these cases, if you take electrophile to be added, then if I put this as R, then electrophile will come at ortho position and para position. And there is some amount of meta position electrophile also, but this will still be minor only. Okay. And all of this is because the first case is because of purely due to the resonance stabilization due to lone pair. Second case is also due to resonance stabilization due to the pi bond present. Like this, it will push, the negative charge will come at ortho and para position. Okay. Last case is due to, these are all due to hyperconjugation, hyperconjugation and plus psi effect. And hyperconjugation and plus psi effect is trying to favor at ortho para positions. Okay. All of you understood which case you will get OP directing here, right? Okay. The next one is about meta directing. Okay, in which case we will have meta directing. Let's see. Meta directing groups, which means if you have benzene, if you have benzene like this with some group G here, and if this group G, sorry, let me put it as a case 1, case 1, if the group is strongly withdrawing, electron withdrawing groups like NO2, like cyanide, like SO3H, these do not have no lone pair group. They do not have lone pair group present directly on benzene. See, why that would happen here is like this. See, N, I have double bond O, O minus, add plus. This is the structure of nitrobenzene. Okay. Now, if you notice its resonance, this pi bond is pushing towards NO2 to stabilize it. So hence, what do we get? We will get a double bond character here with O minus plus charge will be there. Correct? Like this structure repeats 3 times. You see, first it will get negative charge here, double bond, double bond. Again, this lone pair can move here, pi bond can move here. So negative charge here, double bond, double bond. Again, the lone pair can move here, pi bond can move here. That way, again, you will get double bond, negative, double bond. Right? Sorry, not negative, positive. Okay. So you can see positive charge is forming at ortho and para position. Because ortho and para positions are more busy with positive charge, would they invite one more positive charge like electrophile here? Not so much. So which means this one, if at all we invite an electrophile, correct? What is the chances that this group G will take electrophile here, or it will take an electrophile at para position, or it will take an electrophile at meta position? Now, chances of these two are less likely to happen, correct? So, only meta will come. Only meta position will come. Okay. Done. That's why if you do not have any lone pair group directly connected to the benzene form, chances of getting any orthopara products is less. Case 2, if you see, case 2, if you have any C double bond O group connected, C double bond O group, on benzene, group on benzene. If you have this group here, then also you will have the same logic, same problem here. That is, I can have C double bond O with H. Likewise, I can have C double bond O with some R group, or C double bond O with some OH group here, OH here, or C double bond O with OR group. So anything after C double bond O, it is always going to be withdrawing. All are all are electron withdrawing groups. What does that mean? See, if you notice on benzene, you have C double bond O, let's say H here. Pi bonds are present here. So definitely this pi bond will move here. This pi bond will move away from it. And that way you will get a positive charge here, double bond, double bond, double bond C, O minus and H. Again, you see this positive charge is actually moving across ortho and para position only. Okay. So once that positive charge will move at this position, and once it moves at this position, therefore these groups also, which where C double bond is directly connected to benzene, you can only expect them to be withdrawing and electrons from benzene. Okay. Now let me tell you, I hope you understood the scenario in these two cases where meta direction is favorable. Okay. Now let me tell you two important terms here. One is called activating groups. The other one is called deactivating groups. On benzene, you can have two types of groups, either activating or deactivating. Simple. If you have a group here, correct, and the group is pushing the electrons here. So this is electron donating groups increases electron density on benzene. Electron density on benzene. Hence, they are activating groups. Activating groups. So in simple terms, electron donating groups are activating groups. Now, if at all there is a group which is electron withdrawing group, so which means it is trying to pull the electrons away from benzene. Electron withdrawing group decreases electron density on benzene. Electron density on benzene. Hence, they are deactivating groups. They are deactivating groups. Clear? So electron donating or electron withdrawing. These two will make activating or deactivating groups. Simple. Okay. Now what we can say, I can write few statements about it. So all activating groups, all activating groups are OP directing, OP directing for an electrophile. If an electrophile is being pushed, it will only favor orthopara directing. Next, clear? All deactivating groups, all deactivating groups are not only meta-directing groups, which means they do not only give meta, some cases they can give ortho para also, even though they are deactivating. Like in the case of, if you notice the example here, like halogens, okay? Halogens have lone pair on it, okay? So if the lone pair is being pushed electrons here, we say it is offering plus R effect. It is offering plus R effect. But at the same time, halogens are highly electronegative by nature also. Hence, they will pull the electrons also. They will pull the electrons also. Hence, it is showing minus I effect also. Minus effect also. Overall, minus I dominates over plus R for halogens. For halogens. Okay. So therefore, overall, overall, halogens are electron withdrawing groups. Got it? Even though they are electron withdrawing groups, they will showcase orthopara directing nature. Okay, this is the fact we need to understand. Clear? Knowing the fact which of them are activating and deactivating groups, we will categorize them into three kinds. Three type of activating, three type of deactivating. Activating includes strong activating, mild or moderate activating, or very weak activating. Likely, we can have a strong withdrawing, moderately withdrawing, and weakly withdrawing. Now, check out which case is what. First one. If we use the term strong donating groups or strong activating groups, got it? So you can see strong donating groups includes Nr2, NHR, NH2, OH, O minus, NH minus. When oxygen or nitrogen both are donating groups, correct? In that case, they are going to be the strong donating towards benzene ring. Now, what would happen if benzene ring is strongly activated? Got it? Then electrophiles will be facilitated much easier. Got it? Now, that's what the list I have written it here. Sorry, where is it? Here, group one. Strongly activating groups. Okay. O minus, OH, NH2, NR2, NHR, OR. Okay. OR is little debatable. In some cases, we take it as strong. In case, some cases, we take it as mild. But if at all I have to compare within these groups, right? Within these groups, if at all I have to compare, the first thing I would say, okay, uh, strong activating groups includes NH minus, that is the most strongest one, then O minus, okay, then anything which has minus, although it does not have any plus R effect, but its my plus I effect is very high, so that is also strong activating group. And then comes Nr2, then we have NHR, sorry, NHR, then we have NH2, and thereafter we will get OH. And only after OH we get this as OCH3. Okay. This is the order in which the strong activating groups are present. Clear? And all of them are on the basis of how easily they can donate electrons. If a group already has a negative charge, that is much easier to give electrons or support the electrons towards benzene ring. Okay. That's why the negative ones always come first, then the neutral ones which are with lone pairs on it. Okay. Next. Second one is moderately activating group. Moderately activating groups, as in they are donating, but at the same time, those donation would happen on both sides. Electrons can be given towards benzene also, they can be given towards C double bond O also. Okay. Here you can see it is like a split resonance. Oxygen is giving here also. Oxygen is donating electrons here also. But overall, we can say the plus M ability of this group is still greater than the minus I group. Actually, they're all showing plus M also. Here also, all of these groups which I have said, they are all showing plus M also, and they are showing minus I also. But I can say plus M is far, far greater than minus I in this case. In the first case, strongly activating groups. Hmm? Hmm. Got it? But if you notice these groups, nitrogen and oxygen containing group this way with OCH3, we can say plus M is still greater than minus I overall. Okay. So you can see lone pair can be pushed here, because of which negative charge will come at ortho and para position. So if an electrophile has been taken, we can say it will come at ortho position and para position. So definitely group 2 will also favor OP directing. Hmm. Got it? Group 2 is all about moderately activating. Group 3, if it comes to group 3, they are weakly activating groups. Weakly activating includes CH3, C2H5, CH double bond CH with electron donating groups, only CH double bond CH2. All of these are weakly activating groups. So what do you mean by activating here? Activating means they are pushing electron density towards benzene. In all of these alkyl cases where they have hydrogens on it, direct hydrogens on it, the hyperconjugation is greater than plus I. Hyperconjugation is greater than plus I. And similarly, if you have only CH double bond CH, its plus M is greater than its minus I, greater than it is minus I, minus M. This is what you would notice. So plus M will be greater. Here, hyperconjugation is greater. So all of these are again weakly activating. Okay. But if you notice group 1, group 2, group 3, okay, all of these group 1, group 2, group 3 are overall activating groups only. And they will favor orthopara directing whenever an electrophile is approached. Next one you can see is mild deactivating ones. Mild deactivating includes fluorine, chlorine, bromine, iodine, NO, CH2Cl, CHCl2 in all of these cases. In all of these cases, minus I is greater than that of plus M. Okay. So in all of these cases, minus I is dominant. That's the reason why they are mildly deactivating. Okay. It will also favor ortho and para position. It will also favor ortho and para position. So you can see chlorobenzene is there. If I take an electrophile here, it can come at ortho position or it can come at para position. Okay. Meta position can also be favorable, but mild, it will be mild activating. Got it? You can see this is the explanation after the electrophile has been attached. When electrophile attaches, positive charge will come here as per ES. Then again, positive charge will come here. Positive charge will come at this position. When the positive charge come at this position, then lone pair will be pushed here to make it more stable. So that's why ortho is always favorable. You can get this as Cl with plus charge with double bond, double bond. We have electrophile and H like this. Okay. Now, what does that mean? You can see, even though they are deactivating, yet these groups will favor ortho and para direction only. The fifth group is moderately deactivating. So wherever you have C double bond O with aldehyde, ketone, acid, amide, ester, acid chloride, all of them. You have C double bond O Cl. All of these kind of cases, these are all moderately deactivating groups. And last one being strongly deactivating. If you have Strongly deactivating groups. Strongly deactivating groups includes NO2, cyanide, SO3H, CF3, anything which has plus charge on it, like NR3 plus, NH3 plus, NHR2, CCl3. They would have, I mean, last these cases, let me correct on this part here. Last these cases will have extremely high minus I effect than any of the other effects, because it does not show any plus m effect. They do not have any lone pair on it. So neither they'll show minus m effect, but their minus I is high, and that's the reason why they would be more effective. While here in these three cases, you will have minus m being greater than that of minus I. They all have high amount of minus I effect here. Correct? So I'll remove this part. Yeah. Okay. So what did we note here? Group 5 and 6 are always meta directing. They will only allow meta positions to occupy. Okay. So earlier I told you how the nitro group has positive charge at ortho and para position. That's why they will favor more from the meta position to attack the electrophile. And same goes with aldehyde also. It will always favor at meta position. Got it? In generally, if you notice, electrophilic aromatic substitution makes very good activating nature if it is electron donating group, then benzene, and then electron withdrawing groups. So overall rate will always be first preference to activating, then to only benzene, and then to deactivating. Okay. So if you compare, for example, here A, B, C, D, E, OH, I would say it is strongly activating group. Strongly activating group. CH3 is weakly activating group. NO2 is strongly deactivating group. Only benzene no effect, and this is weakly deactivating group. That's why if you notice the rate of the EAS reaction, the first will be strongly activating. Out of this, most strongly activating is OH group. After OH comes CH3, so A and B. Then only benzene is better than chlorobenzene than compared to nitrobenzene. So D is better than E, and least will be C. Nitrobenzene will be the most withdrawing group. That's why it has, least amount of rate of ES. I hope this is clear to till this part. Six groups, everybody. And believe me, lot of questions in JE, they are all dependent on these six groups only. So be very clear about which group comes in which category, right? Based on that, you should know which one will have a faster rate or a slower rate, because all the questions are related to that only. Okay. So now you start comparing. I'll give you the first five examples, everybody. Please check it out. Try it out and see comparatively which one has a higher rate and why. Okay. So please try the first five. Okay. You would notice that the first three, in fact, are very strongly donating. The next two are moderately donating. Okay. Next comes NO2 is very strongly withdrawing. So because it is strongly withdrawing, out of all the cases, A will be the least. Then comes B and C. This you got to remember. Between these three, highest is NO2, then cyanide, then SO3H. It comes directly on the basis of electronegativity which is connected. That is, nitrogen is most electronegative, then carbon, then sulfur here. Because this carbon is basically which is sp hybridized, so it will have sufficient electronegativity on it. And thereafter you will have COOH is also withdrawing, chlorine is also withdrawing, so therefore D, then E, then H, sorry, then F, which is H in this case, and CH3 is actually donating, right? So CH3 is donating, so that will be better than all of them. Okay. Correct. Next one, ABC. More the withdrawing group. There is one chlorine, two chlorine, and three chlorine. Okay. So you can see More the number of chlorines, more is a withdrawing nature. So therefore C will be less than B will be less than A. Next one. This is very important here. So basically, in this case, you would notice benzene with CH3 here. CH3, it will have three hydrogens. So all three will be hyperconjugating. Here, C2H5 has two hydrogens. Here you have only one hydrogen. Here there is no hydrogen. So more the hyperconjugation, more is the uh, activating nature. So therefore, A will be more, then B, then C, then D. This is the order you must know. Okay, based on number of alpha hydrogens on it. Next one, we have OH, OCH3, CH3, H and chlorine. In this case, you know that OH is a very strongly activating, then OCH3, then methyl, then hydrogen, and least comes chlorine. Now, in the case of fluorine, chlorine, bromine, and iodine, what has been noticed in case of these four, what has been noticed is that fluorine, see, if you have fluorine, correct? Fluorine is offering its lone pair towards benzene, and that is making them plus M. But it is also pulling, that is making them minus I. Minus I is greater than plus M. But here minus the plus M which it is making is between 2p and 2p overlapping. What does that mean? There is this lone pair is present in 2p orbital, and the pi bond here is also 2p. So if it is between 2p and 2p overlapping, correct? Between 2p and 2p overlapping, that overlap will be better as compared to that of chlorine case. You will have chlorine like this on a pi bond. Here we will have 2p of carbon and 3p of chlorine. So here also plus M is there, minus I is dominant. But if you compare the plus M of fluorine versus plus M of chlorine, the plus M of fluorine is better offering. That's the reason. Overall, if you notice the electron withdrawing nature, okay, overall electron withdrawing nature, if you compare, then definitely iodine is most withdrawing, then bromine, then chlorine, then fluorine. Electron withdrawing nature. If electron withdrawing is more, that means rate will be less. Hence, rate of reaction will be better for A, then B, then C, then D. See, other than benzene, normally if you have halogens, right, directly halogens are connected to alkyl group, we say that fluorine is more withdrawing. It will offer more minus effect. That's why. Here, you need to check out overall effect. There is plus M also happening, minus I also happening. The overall effect is more withdrawing for iodine. Okay. Finish with these three cases. So I hope all of you understood 1 to 6. Right.
So,
Yes, but any doubt?
yes,
Anish,
on the second, how did you classify hydrogen?
how did we classify which one?
Hydrogen, H.
H. See, H means benzene. Only benzene.
Okay,
Okay.
right, right.
If you compare benzene versus CH3, then CH3 is donating, right?
Hmm.
Correct. So that's why donating is better than no effect. Okay.
Okay,
You know.
yes.
Next, let's understand this position of electrophiles on benzene. Where do they actually? Uh, this I want all of you to do it along with me. Okay. The practice is very essential for this case. Suppose if you have a naphthalene and electrophile is going around, then which all positions it can go? Check out. There are two distinct position of naphthalene. One is the alpha position, one is the beta position. Okay, clear? One is the alpha position, the other one is the beta position. Now you see when it comes to alpha position here, how is it located? See, suppose if an electrophile goes here like this, Then positive charge will come here, double bond will be here, correct? This is when electrophile is present on alpha position. Second, if electrophile is present here, then this is the one where positive charge will come, correct? Correct. Now notice in the first case, what are all the resonating structures I can make? In this case, I can make one double bond here, positive charge will come here, one electrophile will go here. This is another resonating structure. In the second case, if you notice, we can have like this and electrophile here, and positive charge has to go to the other ring and double bond should come here this way. Now, see the problem here is in the first two cases, of course, I can write more resonating structures. I'm not writing them. It's not required. Why? In these two cases and these two cases, if you compare, at this position, you notice this ring is still, one ring is still aromatic. That is, you can see the left side of the ring is still aromatic. Here, this side of the ring is also aromatic. While in the second case, this is still aromatic, but here there is no aromaticity, which means you have two aromatic rings retained if at all we are making an substitution at alpha position. But you are getting positive charge, I mean, you are getting only one aromatic ring if you have it at beta position. So at beta position, if you have, you can see electrophile will be present at this position, at beta position, positive charge will come at this position. So hence, you would notice that in the first case, the intermediate is more stable than the second case. Okay. So we can say the alpha, the electrophile here, that is, uh, let me write down this as 1 and 2, 3 and 4. Okay. So 1, 4 intermediates would always be more stable than 3, 4 intermediates stability wise. Hence, if an electrophile approaches, the major product will be first on the alpha position and then on the beta position. So if it comes to stability, 1 and 2 are greater than 3 and 4, and major product will be 1 or 2. Okay, so I mean 1 or 2 are same group, 1 or 2 are major products only. So I'll just write down alpha is major than beta. Alpha is major than beta. Clear? So I hope all of you understood what happens in naphthalene case. In naphthalene case, alpha is greater than beta. Chalo, next. If you notice the pyrrole case, pyrrole also have alpha and beta positions. And if an electrophile goes across, so what is the product you can get? Check it out. We have N here, double bond with an electrophile and positive charge. Similarly, I can have NH here, sorry, NH here, double bond here, positive charge coming at this position. Lone pair is here, electrophile is here. Another resonating structure is N double bond H with a positive charge coming on nitrogen like this with an electrophile here. So how many resonating structures we are getting? 3 if it is at alpha substitution. Next, if it is at beta substitution, so NH, if this is a beta substitution, electrophile is here, positive charge is here, okay, and double bond is here, lone pair, and then nitrogen can make a double bond here with a positive charge and electrophile here, double bond here, correct? Now, if you notice one more resonating structure means you can have like this double bond here, okay? So that means this double bond moving here, right? Now, do you think this nitrogen can hold 5 bonds here? Not a chance, right? This electrophile does not exist, correct? Nitrogen can't have that positive charge on it. I mean, sorry, nitrogen cannot have 5 bonds on it. So therefore, if you compare the number of resonating structures, when the alpha substitution happens, you're getting 3. When beta substitution is happening, only 2. So therefore, stability wise, if you compare 1, 2, and 3, 1, 2, and 3, here 4 and 5. So we can say stability wise, then 1, 2, 3, these are the intermediates which are better than 4 and 5. So major product will be again alpha greater than beta. So whenever an electrophile has to be substituted on pyrrole ring, you will always substitute at alpha position more than beta position. Is this logic clear, everybody? Yeah, right. Next is the case of pyridine. Check out in the case of pyridine what is happening. In the case of pyridine, we have alpha, beta, gamma. So nitrogen with an electrophile here with a positive charge here this way. This is when you have an alpha substitution. Okay, and then that that lone pi bond can keep moving to make resonating structures like this. Okay, and again double bond here, correct? And positive charge is in fact coming on electrophile, I mean on nitrogen. See, getting a positive charge on nitrogen will not be that good. I mean, it will not give any stability as such. So therefore, the formation at alpha position less likely to happen maybe. Let's see about beta position. If you get an electrophile here, positive charge will be here. Lone pair is here like this way. Okay. Then obviously, if this lone pair comes in resonance here, which is not possible because both of them are in opposite direction. Let me show you structure wise. Structure wise, if you notice the pyridine structure, this is how it is. One lone pair is in this orbital, while all the pi bonds are in this orbital. So lone pair in pyridine cannot participate in resonance. Please keep that in mind. Okay. So this lone pair is perpendicular to that of this orbital. So this cannot be participating in resonance. Okay. And that's the reason why here it cannot happen. Hence, you can see positive charge at this position. Uh, you can have resonating structure this way without involving the lone pair. Positive charge can come here like this, and again double bond, and positive charge can come in this position. So how many we got? 3 resonating structures, but without getting a positive charge on nitrogen. So that is good. Okay. Same way, if you compare for gamma, okay, in the case of gamma here, we'll get positive charge here, electrophile here, double bond with a lone pair. And that positive charge, if it goes on here, we will get positive charge on nitrogen. Again, positive charge on nitrogen is not favorable. Hence, if you compare the stability here, correct? Of course, you'll get one more resonating structure where you'll get double bond here with positive charge here like this. So you will notice that alpha position and gamma position are the same, but their stability is weaker than beta. So major product will be beta more than that of alpha or gamma. This is the major product. So please check pyridine. So I would request all of you to please check 1, 2, and 3 if you have understood all the cases. Next thing, if the reactivity is being asked, like which one is more reactive, and if an electrophile goes, where does it attach? If you're comparing benzene versus pyrrole, correct? It's evident that the pyrrole has lesser resonance energy, so it is more reactive. Resonance energy is less means stability is less. Sorry, yeah, stability is less, which means it is more reactive. So if you compare the pyridine is more pyrrole is more reactive. So hence 2 is more reactive. Therefore, electrophile should be always given more priority to pyridine ring rather than benzene ring. Okay. And next, if it comes to benzene, if it comes to benzene versus this ring, you can see uh, between the benzene and pyridine, although pyridine has lesser resonance energy, because it has to gain through positive charges, which is very close to nitrogen, electrophile would be reluctant to attach either at alpha, beta, or gamma position compared to benzene. So this is an exception. That's why I marked it. You can notice that. So it is an exception where benzene overpowers the uh, pyridine case. Clear? So one is more reactive than the two because pyridine cannot handle this positive charge better than benzene. Okay, nice. You can see if it comes to indole, indole is a combination of a benzene and pyrrole. So if an electrophile has to go between these two, which one should be given priority? We should give priority to pyrrole. Just now we learned. So within that pyrrole, between alpha and beta, we learned that alpha is stable than beta. So what is a major product here? You will write the major product as this one. So here is the electrophile. That will be major product. Okay. If you are asking for the minor product here, sorry, in this case, if you notice a minor product, it will be like this. Here we have N double bond like this, and electrophile goes here. So this is major and this is minor. Next, if you have an electrophile where you have a benzene ring and pyridine ring, both of them, and we just learned that the priority should be given to benzene. So one electrophile here, 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 and here. Okay. Out of these, the electrophile where the nitrogen's positive charge and electrophile's positive charge here will be very far away. In this case, sorry, I wrote both of them at the same position here, like this. So if you compare, then this last case is the one where the positive charge will be far away from nitrogen, hence that is major product. So this one is major product. Okay, so I hope these three cases are clear. Next, if it comes to anthracene, anthracene has three benzene rings connected with each other. If an electrophile goes, there are mainly two positions which are, three positions where electrophile can go. One is this one, and one is this one, and one is this one, and the other one is this one. So this with positive charge here, and positive charge here. Okay. So you can notice between these three, when an electrophile approaches, in the first case, these two benzene rings are preserved. While here, these two benzene rings are present, these two benzene rings are present. But if you recall one thing, if you compare to two isolated benzene rings, that will have more resonance energy than a fused benzene ring. You can see fused benzene ring will have resonance energy of 270, but isolated will have 298. So which one is better? First one is better. So that's why electrophile will always get attached on the central carbon here. Okay. So I suppose this part is clear, everybody. So intermediate stability wise, one is more stable, then two and three will have similar stability. Got it? Sorry, uh, my mistake. Between these two, we already discussed that three will have more stability than two. Okay. And major product will be this one here, an electrophile. Okay. and positive charge coming at this position. This will be major product, which means electrophile will come here, and overall you can see once the electrophile get attached here, so we can say double bond at this position, double bond at this position. This is the major product. Now notice, if reactions are happening on a functional group present on benzene, like see, there is benzene and another benzene which has OH on it, which is basically, this is called alpha naphthol. Okay, this is called alpha naphthol. In the case of alpha naphthol, when you have to do bromination, for example, then between benzene ring and phenol ring, which is more activated, this phenol ring is more activated, correct? We learned it already. So in this phenol ring, we have alpha, beta, gamma positions here. I mean, ortho, meta, para positions. And we know that OH is OP directing. So we will get bromine at this position and bromine at this position. These two are the major products which you will get. Okay. Acha, within the alpha and within the ortho and para, if you have to compare, usually para is always major unless there is some stabilizing factor coming into picture. So therefore, generally speaking, in all the cases, you will always go for para product because of its less crowding nature. Okay. I hope all of you understood that between between ortho and para position, give priority to para. Similarly, here, there are three rings here. Notice it carefully. There are three rings here. In these three rings, if you compare, right, this ring with NH2 is more activating. This is not activating. This is deactivating. So obviously, your priority should be about activating ring. Within activating, the ortho is already occupied. So para is only left. So where should be the bromine coming? It should come at this position. This is major. This is major product. Okay. And that is the only product you will get. It's not like we'll have major minor here. In fact, that is the only product. Reason is simple. Here ortho is occupied, here ortho is occupied. Next, between benzene and NO2, you can clearly notice that bromine can come at, I mean, this is deactivating ring, so nothing will happen on that. This is activating ring. So with that activating ring, Br can come here. That is major product. Clear? Next. If you notice the next one here, there are two benzene rings across the COO group. Across this COO group. Now, across this COO group, if you notice, this side ring is activating while this side ring is deactivating, because this side, when you have C double bond O connected, we just learned it, it will pull the electrons from benzene and make the benzene deactivated. Correct? Therefore, this is deactivating, this is activating. Hence, bromine will always go on the activating side. So, within that activating side, we have ortho and para. But like I said, para is always given priority, that is major product. Okay, this is major product. Next one. If it comes to biphenyls, these are called biphenyl rings, nitro biphenyl. In case of nitro biphenyl, see, nitro usually we learned that it is deactivating. So deactivating should, give more priority on meta. This is meta, this is meta. For this ring, now this is meta, this is meta. But unlike going for meta in biphenyls, it is going for para position. You can see this is the position, and that is where you will get the major product. You are getting Br here, and that is a major product. I mean, even though NO2 is a strongly withdrawing, still you are getting para as major product. Let me explain you through these examples. Check it out properly. Okay. Suppose if it comes to an group present here, right, and then an electrophile is present here, no? What would happen? If an electrophile is added at the para position, correct, you would notice that positive charge will be here, pi bond will be pushed here, positive charge will come here. Pi bond will be pushed here, positive charge will come here. Pi bond will be pushed here, positive charge will be coming at this position. Pi bond will be pushed here, positive charge will come. Pi bond will be pushed, positive charge will come. Pi bond will be pushed, positive charge will come. Have you noticed that we are able to generate at least this 7 to 8 resonating structures, correct? Keeping this at para position, correct? So, keeping it at para position, there is an advantage. What is it? You are able to generate maximum number of resonating structures. But imagine if you keep it at meta position. If an electrophile is here, positive charge will go here, it will go here, it will go here. This ring is not involved only. Let me show you here. Check out. If an electrophile is here, positive charge is here, that will come here and that will come here. This ring is not involved at all. So here you will not notice on the basis of OP directing or meta directing. Okay. Here you will judge only on the basis of number of canonical structures it can make. So you can see the resonating structures are maximum in the case of para position. Hence, even though there is a withdrawing group or there is a donating group, NO2 is withdrawing, OH is donating. In both the cases, para is only major product on the secondary. Very, very important case, everybody. Look into it, 5 and 6. Okay. Okay. I hope all of you got that. And next thing is CCl3. CCl3 is strongly withdrawing, so it will only go for meta position. So we are 100% will get only this product. You will not get any other product. Clear? Then, right, everyone, please go through it once quickly. Next, let's see one by one name reactions. First one is Gatterman-Koch reaction. How does this work? Let's see how the structure of carbon monoxide is. So we know that it is C triple bond O with minus and plus, right? And we have HCl here and AlCl3. So this is how it works. Cl will attach to aluminum, the bond will break, C minus will take this H plus. That's how we will get H, C, triple bond O plus charge plus. Next we have AlCl4 minus. And then benzene will attack on this part. We have H, C, triple bond O plus. So pi bond will attack here. This group will move, and that's how we will end up getting aldehyde, right? So this is via ES. This ES mechanism we don't have to write again and again. We know how stepwise it will happen. Got it? Clear, everybody? So this is the mechanism that will take place. What you need to realize is this AlCl3 should be anhydrous. Okay, because breaking of HCl, if it is in aqueous solution, then this will not happen. It should be always in anhydrous solution so that only Cl minus can go, and aerially the C minus will attach, because carbon monoxide is actually neutral in aqueous solution. So it will not make any reaction otherwise. Got it? This is about Gatterman-Koch reaction. Okay. See, hydrolysis is the step that would help in case if at all we have this aldehyde getting O minus or so, but usually this is not a step necessary. Okay. Mhm. Next. Sorry, one second. I'll come back to the second case. First, let's come to the third case here. Let's see what is deuterium case, right? So basically, if you have D3O plus, so what will it do is that wherever there is hydrogen, it will replace that with deuterium. Okay. Just like in tautomerism steps we do, here also deuteration will happen. Okay. So you will get this as hexa deuterobenzene. Hexa deuterobenzene. That is what you will expect on excess amount of D3O plus. Second, addition reactions. You see, if you take ranitidine, benzene is very less likely to react uh, uh, directly with any H2 addition. So H2 addition does not happen that easily. But if you are reacting that in the presence of high pressure and temperature, then the reduction will take place, and you will notice that you will get this as cyclohexane. So cyclohexane is a major product here. Okay, these two does not need any mechanism steps here. You just need to remember directly what would happen. Next, if you compare the radical mechanism, check out benzene when you react with Cl2 with H nu. So it's a very typical radical mechanism. Cl dot will form and Cl dot will propagate on benzene. So hence we will get this as chlorobenzene like this. One, if you have one chlorine being added. Now remember this carefully. If you have less amount of chlorine here, correct? So which means it will go for substitution more than addition. So it will undergo substitution more than addition. But if you have excess, for excess you will get addition more than substitution. So you will get this as Cl, 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 Cl and Cl. So this will be radical addition. Radical addition is favorable. Got it? Next. In case if you have toluene, instead of benzene, if you have toluene, that is, if you have a methyl group on benzene here this way, in such case, you will notice that with one equivalent of chlorine, you will get radical substitution on benzyl. Why? If you compare the stability of CH2 dot versus phenyl ring, that is benzene ring dot, you know that this radical is more stable. Benzyl radical is more stable. That's why chlorine will go here. And with aqueous NaOH, chlorine will be replaced by OH. So you will get this as CH2OH. Okay, known as benzyl alcohol. Benzyl alcohol. Next, Cl2 of two equivalents. If you take two equivalents, you will get CHCl2. And CHCl2 replaces two chlorines here. That way you will get two OH. And two OH groups are unstable on the carbon here. So that makes it into an aldehyde group. So you'll get CHO. So what do we get? Benzaldehyde. We'll get this as benzaldehyde. Get this as benzaldehyde. Next, if you have three chlorines here, then you will be replacing all three here. So CCl3, and with aqueous NaOH, you will get all three OH getting replaced, which will convert into a benzoic acid. Read as COOH. So what do we get here is benzoic acid. Then these are few radical based mechanisms, right? Either it is benzene or toluene. In both these cases, this is the product you will get. Okay. Next, when it comes to toluene, another important reaction is about oxidation. Okay. If you have a toluene and it get oxidized, the surface carbon will get most oxidized and that will convert up to benzoic acid. The oxidizing agents used for this to happen is KMNO4 in basic medium or acidic medium or K2Cr2O7 concentrated HNO3 All of these reagents will make it. Okay, no mechanism needed. You just need to remember these reagents directly. Wherever you see carbon above, you can convert that into carboxylic acid. Now, in which all case we need to convert that into carboxylic acid, notice that carefully. Suppose if you have all three methyl groups attend and there is no hydrogen at all, in that case oxidizing this carbon is very challenging, so no reaction will take place here. Okay, so you can see above benzene ring must have at least one alpha hydrogen for oxidation to happen. Okay, so KMNO4 usually it will give nascent oxygens in acidic medium or basic medium. That nascent oxygens require at least one hydrogen to get inserted. And once the insertion happens, it will start breaking all the sides and convert into benzoic acid. Typically, this is how it will happen. Now, notice here also in the next phase, when you have ethyl, there are two hydrogens here. So, we require at least one hydrogen. So, you can see between these two hydrogens, the oxygen-oxygen bond will come here. I mean, these hydrogens will be replaced with OH groups. And any carbon that is attached will also break, and single carbons will convert into carbon dioxide. So, you should always break it this way. Convert this into carboxylic acid. The last carbon should be converted into carbon dioxide. Same logic here, break it here, convert this to carboxylic acid. Two carbons will again convert into benzoic acetic acid here. Same way here also there is one hydrogen, so break it here, benzoic acid and 2 moles of carbon dioxide. Here also break it here, benzoic acid, 1 mole of carbon dioxide and 1 mole of acetic acid. This one is acetic acid. If you have a double bond, there is no compulsion of having a hydrogen here. If carbon already have a double bond, then this necessity of having alpha hydrogen is not, required. So you can break it directly, benzoic acid plus CO2. Here also break it, benzoic acid and 2 moles of CO2. Here also, these two carbons can be converted into acids. You will get phthalic acid. Here also there is one hydrogen. Here also there is one hydrogen. Both sides you break it, you will get benzoic acid. These two carbons will convert into oxalic acid, and this single carbon will convert into carbon dioxide. Okay, so these are all the forms which you can get. Next, if you have a triple bonded carbon here, you break it, this carbon will convert into benzoic acid, and this side it will convert into acetic acid. Okay, so that is similar to all of these cases. Everything will convert into benzoic acid. Okay, so I think it's a little heavy for you. Please check it out carefully again. All of the cases one by one, everybody. Check from B case onwards. Check out till H case first, G case first. Next important concept in this benzene is OP ratio, ortho-para ratio. Okay, that is if you have any uh, X group, okay, any X group and electrophile has been added. So where does this electrophile go? See, electrophile can go at ortho position or para position if it is OP directing group, correct? But how much, whether the ortho becoming major or para becoming major, how do we assess this? So check this out. Percentage amount of ortho found to be similar in at similar conditions, which means if I keep fluorobenzene, chlorobenzene, bromobenzene, iodobenzene, all of them at room temperature, let's say. At room temperature, the percentage amount of ortho was found to be around 12, 30, 32, 38, which means the minus I is more influential. So minus I of fluorine is greater than chlorine, greater than bromine, greater than iodine. So you can say that minus I is more influential. Minus I is more influential in this case. Okay. Next, if pi bond attacks on this electrophile in the presence, I mean, if you have it in fluorobenzene, then definitely you'll get electrophile here, correct? And another one is electrophile here at para position. And since this is only 12%, rest of the 88% will be ortho. So this will be major product. In fact, for all the halogens, sorry, for all the halogens, if you notice, in all the case of halogens, you will find para is always the major product. You can see even still iodine also it is only 38%. So therefore, para product is always the major product in this case. Clear? Right. Check. Next. When strongly activated groups are present, right, multi-substitution can take place, right? This was the first case which I left it. Now, after teaching this, I'll go back to that case there. Check out. In case if you have a phenolic group, OH and NH2 are very strongly activating group. So, if you have OH and NH2, so in the case of phenol, if you treat with bromine and CS2, right, it's a very normal condition. So, where we can say bromine can come at ortho position as well as para position, and para is major. But in case if that instead of bromine CS2, if you have bromine water, in such case Br plus is available in this case, and Br plus is in rich amount. What does that mean? See, the reaction goes something like this. We have H2O plus Br2. It will form HOBr plus HBr. And HOBr will have H minus and Br plus. So the Br plus concentration is rich amount. Br plus concentration is in rich amount. So because it is in rich amount, we can get this at ortho position or even at para position, right? So all the ortho para are open for that. So therefore, bromine, bromine, and bromine will come at this position. So you'll get this as 2,4,6 tribromo. Okay, 2,4,6 tribromo benzene. This is what you will get. Sorry, phenol, not benzene. Tribromo phenol. Okay, this is major product. Okay. Achha, this is a white PPT by the way. This is a white color PPT. Color PPT. I'll read that also. Precipitate. Next. In case if you have nitration with dilute HNO3, same thing. NO2 presence will be in a very small amount because amount of NO2 is in less quantity. We can say that we can get NO2 at some amount of NO2 at ortho, some amount of para, and para is usually major. But while if you take NO2, if you take concentrated H2SO4 and then concentrated HNO3, we learned this that this is a nitrating agent. So due to nitrating agent, now the NO2 plus quantity available will be large, and therefore you will get NO2 quantity will be heavier at all three positions. Correct? And this is called picric acid. Picric acid pKa value is around 1. Very strongly acidic. Okay. It's one of the strong acids, everybody. So when you have phenol with dilute conditions, this is the product. With concentrated conditions, picric acid is the product. Okay. Next. If you notice, say, when it comes to NH2, even though bromine amount is very less here, Br plus, in fact, Br plus is not present only. Here, Br plus quantity is less. Okay. Because CS2 is this is non-polar. This is non-polar. So in non-polar, you will not see bromine getting dissociated. Hence, bromine will not be in large quantity yet, everybody. NH2 is a very strongly donating group. Hence, it will activate at all the positions for bromine. Therefore, you will get again a white PPT, white precipitate here. The product what you will get is 2,4,6 tribromo aniline. tribromoaniline. This is the product you will get. Okay. So you could notice that with even a non-polar solvent with less Br only you are getting. If you have polar solvent and large amount of Br plus rich here. So here Br plus quantity will be large amount. In that case, definitely you will get 246. So this is a differentiating factor between phenol and aniline, everybody. In case of phenol, you will only get ortho or para with dilute amount, sorry, here with CS2. But in the case of aniline, in both the cases, you will get 246 tribromo. And next, with dilute HNO3, in the case of NH2, we will get ortho and para only, just like this. But with concentrated, here is the interesting fact. Instead of getting all three NO2s just like in phenol, here you will get some quantity of ortho, para, and meta. Okay. In fact, you would notice that this is around 47 percentage. This is around 51 percentage. Clear? And rest of the 2 percentage is this one. Okay. Now, if you notice why this one is happening, why something like this is happening is because when it comes to nitration, we are forgetting the fact that you are adding an acid towards a base because aniline is a base with a lone pair on it. Okay. So what would it will do? Or what will it do? It will start showcasing its basic character by taking the proton. It will convert into NH3 plus. So large, I mean, sufficient amount of quantity of aniline will be converted into this form. So in the solution, you will have approximately 50% of this anilinium ion. How do we read it? You read this as anilinium ion. And here it is aniline and anilinium ion. Okay. So you would have large quantity of these two. And you know that anilinium ion is a, deactivating group. So because it is deactivating group, when you do nitration, so it would go at meta position. It will go at meta position. Therefore, you will see NO2 at this meta position, and that will be the major product. Okay. Again, this is different in the case of phenol and in the case of aniline, right? In the case of phenol, this problem does not come, right? Because phenol itself is acidic, so that will not get protonated easily. Done. So please go through these two reactions, everybody. Please check. When you have strongly activating groups with phenol and aniline, what will happen? Check quickly. If you take aniline and react that with anhydride, so in that case, what would happen is the lone pair present on nitrogen itself will attack here to get NH C double bond O CH3. Correct? So we will have this as CH3 C double bond O C double bond O CH3. This is how the compound is, right? So this oxygen basically will get connected with AlCl3, and therefore the lone pair from nitrogen will attack directly on this carbon. That's how you will get this form. And CH3 COOH will be later separated out and AlCl3 will be separated out. Okay. The product what we got is an acetyl group on aniline. Acetyl group on aniline has a common name acetanilide. This is called acetanilide. So we will get an acetanilide. Now what happened is, if you may notice that NH2, which is a very strongly donating group, correct? Now because of NHC double bond O, because of this NHC double bond O CH3, this being resonance stabilized on both directions, it is mildly activating group or moderately activating group. You know that moderately activating groups will not make bromine to attach at all the positions. Hence, you will get NH C double bond O CH3 with bromine coming at para position here. And thereafter, if you hydrolyze it, amides on hydrolysis will convert back into amine with Br, and the CH3COOH has been gone. Okay. So you can see this is the major product. Clear? So this is one way if you want to get aniline to only this product, which was not possible earlier, correct? Because this was not possible due to bromine water, uh, attaching in all the positions, 2, 4, 6 at all positions. But if you notice in this case here, we can see it will happen to go at para position here. Clear? Right. Next. Similar logic happens with concentrated H2SO4 also. If you notice with concentrated H2SO4, phenol with sulfonation will take place, SO3H this way. And SO3H happens at two positions, not at three positions. If you take excess, let me put this as excess here. And after this, when the bromine has to happen, you will notice that the bromine will only come at ortho position. This SO3H will be present like this. And if you recall during the preparation, I told you, if you have SO3H and you make dilute H plus, desulfonation will take place. That means sulfur trioxide will go away and we end up getting only bromine here and 2 moles of SO3 will come out. Okay. So therefore, this is major product now. Again, this was not possible to get only ortho position as major pos. It was not possible. But if you use that with excess H2SO4, this had become possible to make the product. Okay. So these are few important reactions of aniline and phenol. Good part is these reactions are highly repetitive reactions in every topic, coming across again in halogens. When we discuss about haloalkenes, then we have phenols, then we have anilines. All of these are a part of syllabus. When we discuss them again, all these reactions will keep coming back. Here we are learning as a part of benzene, but again they will come back. So if you know once, next time when we read, you will be able to recall them easily and hopefully you'll be able to remember it. Okay. Now, when you have nitration, see, you know that in the case of nitro group, you can have chlorine substituting at ortho position. Sorry, chlorine substituting at meta position, and that is the only product you will have, right? So this is the only product. But because NO2 is a very strongly withdrawing group, you will not be able to see any alkylation or you will not be see any acylation either. So no alkylation, no acylation happening here. Okay. Because NO2 cannot be used in alkylation and acylation, it is usually used as a solvent in Friedel-Crafts reaction because it is inert. In Friedel-Crafts reaction, nitrobenzene will not do anything. And since it is an inert compound here, we can use it as a solvent in Friedel-Crafts reaction. This has been asked multiple times, an important statement, so learn that. Clear everyone? Right. Okay. So that's it. This is the EAS reactions of all the monosubstitution. That means single functional group present on benzene. How do we need to assess the EAS reactions?